We're now going to go over question 2, which is sort of just like a collection of, I don't know, like trivia, like random questions. It's kind of fun. So question 2A says, suppose that we consider two words to be equal if they have identical definitions in some specified dictionary. For a hash table of words, which of the following could be correctly used as a hashing function? And so in each case, the hash function is called with hash k b arguments, where k is key to be hashed, some word, right? And b is the number of buckets that we have in our hash table. Assume that all words and definitions are non-empty strings, and performance here is not an issue. So that means we're not really worried about our hash function being like good or high quality. It's just whether or not it's valid at all. And so the main takeaway from this is just that two words are equal if they have the same definition. And the important thing with a valid hash code is that equal objects have equal hash codes or the same exact hash code. And so the main thing is that if two words have the same definition, they need to have the same hash code. And so if, let's say we have two words, I'm trying to think of two synonyms. Let's say like tall and giraffe, and they both have the same definition, which is, I don't know, being tall. You know, you get the idea. They're different words, but they're the same definition. So we need them to have, they'd be considered equals according to the dot equals method. So they need to have the same hash code. And so I think it's always really helpful for the hashing questions to like have an example to look at. And so we can see right away, option A, if we take the length, that's going to say that they're not equal or they won't have the same hash code, but they are equals. So A does not work. What about the first character? Again, doesn't work. What about the length of the definition? Well, if tall and giraffe have the same definition, then the lengths will be the same. Therefore, this one works. And so equal objects have equal hash codes. The other thing we're checking is that no matter how many times you hash it, it will never change. It's always going to be the same, right? It's deterministic. And we see the definition is not going to change here, so we're fine. Then we have the first character of the definition. And so again, that works, assuming that these two words have the same definition, then they're going to have the same first character in that definition. So D works. Then E says, let's take the standard Java string hashing function and apply it to K. But again, that's not taking into account the definition. And so these words that are considered equal to us would not have the same hash code. However, if we apply that string hashing function to the definition, then it works. And so this question honestly was pretty much just making sure you realize if we are testing equalness using some attribute of an object, the hash code better be a function of that attribute and that attribute only, like no other attributes. And that's 2A. 2B is a little interesting. It says, let's start with an empty binary search tree that contains integer keys, and we'll add the values 5, 4, 10, 9, 15, whatever, until we get to some number after adding n values of that pattern. How long does it take to add those n values in total? And so if I saw this question on the exam, I would first think, well, what happens when you add these, right, initially? And so if you start with 5, then you add 4, that goes as a left child because it's less. Then you add 10, which is a right child because it's greater. Then you add 9, which is goes to the right of 5 because it's greater than 5, and to the left of 10 because it's less than 10. Then you do 15, which goes to the right of 5 and to the right of 10. Then you add 14, which goes to the right of 5, to the right of 10, and to the left of 15. And so what we realize is that if we do this pattern where we do 5k, which moves us to the right, and then 5k minus 1, which gives us a left child, we're going to end up with a really spindly tree that looks like this, right? And that is no good. And so recall that what we said is that this is really just the same as adding to the end of a linked list, right? We have to just traverse all the way down, comparing at each step. And so when you have a spindly binary search tree like this, we don't get that nice log n runtime that we're aiming for. Instead, what we get is linear because we have to traverse through all of the elements, or almost all of the elements here, right? Technically, we're looking at like half of them if we're always comparing to the right, but still n over 2 is n. And so we see that for each element, we have to look at around n values. And we do this n times. So if you're roughly adding n value, if you're adding n values and each time it takes n comparisons, in total, that's going to be n squared work. And that is the answer to this problem. So a little fun, tricky little binary search tree problem. Then we have 2C, which says after we've added those n values, so I'll actually bring that picture back. After we've added those, how long does it take in the worst case to check whether a certain value k is in the tree using the usual search algorithm for binary search trees? And so what we know about the usual algorithm, right, is that the worst case depends on the height of the tree. Because in the very worst case, we're asking, let's say, for the largest element in the tree, which is going to be all the way at the end of this linked list, which means we have to traverse the whole height of the tree, which here is roughly n. And so to find a single element in this very spindly tree, in the worst case, it's going to be theta n. Note that the best case would be, if it's at the root, right? If the element we're looking for happens to be very small, like 4. But again, this question specifically said worst case. Now we have part D, which says, let's start with an empty binary search tree B of type BST, and assume that the array A contains n distinct values in strictly decreasing order. So how long does this function call basically take in the worst case using our usual binary search tree insertion? And so basically we have this sorted array. And if we look at the atom function, I see what happens is that we first take, let's see. So we pass in the arguments B, which is a BST, our array A, which is n long, and then we start with 0 and n passed in here. Now, L is not less than U, or our lower is not less than our upper, is what this is sort of short for. And then we're going to say our midpoint is L plus U over 2. So initially that's n over 2. So we're getting the middle element. Then we insert that into this tree object. And so let's say, let's try to draw this out. So first our binary tree is empty, and then we add n over 2, which is the midpoint. Then we make 2 recursive calls, which pass in the same tree, the same array, but this one goes up to 0, n over 2, and this one does n over 2 and n. Well, what will this call end up doing? It's going to take the midpoint there, which is n over 4, and add that to the tree, and that'll go to the left. And this call will take the midpoint of this, which is 3/4 n, and put that in the tree. And that's greater than n over 2, right? So it goes to the right. And then what would their recursive children do? Well, this one would do n over 8, and this one would do, shoot, I'm so bad at math, guys. I think it's 3 n over 8, I think. And then this one would be 5n over 8, and this one would be 7n over 8, I believe, if you look at the recursive calls made by the children. But regardless of the actual math or like the actual numbers being passed in, what we see is that we're inserting the values into the tree, and sorry, when I say n over 2 here, I mean the value at data of n over 2. And we know data is sorted, right? So that's going to be the midpoint of the data, basically. And so because these elements sort of correspond to some like sorted order, we realize they're being added to the binary search tree. And it's perfectly balanced because we're adding first the midpoint, then sort of the halfway point between the midpoint and the ends, and then more and more and more and so on and so forth. And we end up with this perfectly balanced binary search tree. And so because it's perfectly balanced, recall that when we add to a balanced binary search tree, that takes log n time. And so if it takes log n time to insert one element, but we're inserting n elements, then this whole function call will take roughly n log n. And so that's the answer here. And so again, I think the main takeaway to understanding this problem is realizing that data is sorted, right? And so we don't know exactly what's in the array A, but we do know that the item at index n over 2 and the item at index n over 4 and index 3 n over 4, relatively, they are all in this sort of order on a number line. And so it is easy for us to like insert them. And I do think I actually might have flopped it because they are in decreasing order. So technically it might actually be the element at 3 n over 4 and n over 4, like according to less than on the left and greater than on the right, because this element is less than this because they're in decreasing. But regardless of the actual elements and where they are, I think the main thing to take away from this is just understanding that, oh, when we add elements in this pattern, the binary search tree is balanced because we're always sort of having our problem and adding the halfway point. And so that is part D. Okay, now we're going to do 2E. And so for this problem, it says, consider a binary search tree that initially contains some values 1 through n, where n has the value 2h plus 1 minus 1, and h is the height of the tree. And so this tree is perfectly balanced, which means its height is h, and all leaves have the same depth, and inner nodes all have 2 children. In other words, the tree looks like this, and all of them are, all the paths are of length h, basically. And so if we have this set up, suppose now we remove all the values from the tree that are not powers of 2, leaving h plus 1 values. In the resulting tree, how long will it take to insert an item in the worst case? And so I think for this problem, honestly, the best way to approach it is to say, well, what the heck does a tree that looks like this, before we remove all the non-powers of 2, what does that look like, right? And there's this hint which is the top node has the value 2h. And so I honestly think the easiest way to do this is to try a smallish example. So let's try h equals 3, which means we're going to have values from 1 to 2h plus 1 minus 1 or 15. And so we know that the root is going to have 2 to the 3, which is 8. And now let's just try adding all these values. So I think, unless I'm mistaken, let's see, 4 goes here. And then 6 goes here, 7 goes here, 5 goes here, 3 goes here, 2 goes here, and 1 goes here. And the way I just did that was sort of taking halfway, 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 right? Almost like this problem, right? Where we saw that we put the halfway point in the middle each time. And so here, h is the halfway point between 1 and 15. 4 is the halfway point between 1 and 8. So on and so forth. And I actually think I messed this up. It's 2 and then 3. And yes, that was right. Cool. And for the other point, what's the halfway point between 15 and 8? I'm so bad at math. 15 minus 8 is 7. What's 8 plus 3? That's 11. It's got to be, I think 12 goes here. Let's try it. Then we have, let's see, 10, then 9, then 11, And then this would be 14, and this would be 13, and this would be 15. Okay, cool. That's a perfectly balanced binary search tree that has the values 1 through 15. If you look at any given value, it makes sense. Everything to the right of 8 is greater than 8. Everything to the left is less than it. Everything to the left of 12 is less than it, and everything to the right is greater, and so on and so forth. So this is our example tree. And now we want to know what happens if we remove all the non-powers of 2. Well, that would mean in this example, removing 3, 5, 7, 6, removing, let's see. Cool. And so we have a tree where the only things that are left are actually this end. And so that's really interesting. We have this tree that's basically a linked list now, right? And the length of the linked list is the height of the tree because it's just sort of one edge of the tree. And so I'm going to take a leap of faith here and say the tree has now just become a linked list of length h, and I'm going to guess that this works for other cases, not just height of 3. And if that's the case, then the time it takes to insert a new item in the worst place would mean traversing all the way down this height and adding the new item at the bottom, which means the worst case is the height of the tree, or h. And that's part E. Lastly, for question 2, we have part F, which says consider a hash table containing non-negative integer keys that uses open addressing, not external chaining, has B buckets, and uses the hash function k divided by 10 times 10 mod B as its hashing function. It handles collisions using linear probing. And in the worst case, we want to know how long does it take to insert a sequence of less than B keys, right? So we're inserting less keys than there are buckets. And they're in the range from 0 to B minus 1, such that any 2 keys differ by at least 3. And so the first thing to make sure we're all on the same page with is how this hashing function works, right? So recall that in Java, if we do division like this, it's going to round down, which means 1 divided by 10, 3 divided by 10, 9 divided by 10, right, would all be 0. Similarly, just to hammer it home, 11 divided by 10, 12 divided by 10, whatever, all of these would be 1. So 10 divided by 10, of course. And so at first, our thought is, okay, this could lead to some major collisions, right? If a bunch of things all lead to the same bucket, because they're all going to be divided by 10 and then multiplied by 10. So this would be 0 times 10 equals 10. Either way, they're all ending up at the same bucket, right? And so the question is, how bad could these collisions possibly be? So let's look at the case where we maybe are inserting, I don't know, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, right? Because theoretically, all of these would hash. When you divide all these numbers by 10, you get 1 because we're rounding down. You multiply by 10 because that's the whole function, and they end up in bucket 10. But here's the thing, we had this guarantee that any 2 keys differ by at least 3, which means in the worst case, we could be putting in buckets, this one, this one, this one, and this one. And so in the worst case, we're only getting about 4 collisions, which is a constant number, and we can manage this. Notice that we're using linear probes with increment 1. And so if we try to put something in bucket 10, let's say we put in 13, and it's already in bucket 10, and then we try something else later, well, that's okay, we'll just try bucket 11, the next thing over. And the other thing to notice is that assuming that B is greater than 10, which is safe to assume because we know n is going to be a big number, right? And b is greater than n. We'll notice that our buckets are going to be 0 times 10, 1 times 10, 2 times 10, whatever. And so our bucket numbers are in increments of 10, which means we have plenty of room for these collisions to linear probe 1 over. Basically, if our array looks like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and so on and so forth, whatever those are array indices, even if we put, let's say elements, I don't know, 7, 4, 3, 2, or sorry, they have to be spaced out. So it's actually going to be 0, 3, 6, 9, whatever. Even if we put all those elements in, and we tried this one, and they were all supposed to be in bucket 0, and we had a linear probe these ones out, all the ones in the range from 10 to 19 are only going to start down here anyways. So there's no problems with these collisions. And so we're seeing it's almost like we're not really having collisions. There's really no problem. Everything is going to be where we expect it to be, or within a range of 4 elements. And 4 is a constant number, which means on average, adding a single element is still constant. And so to insert n elements, where each one is constant, will take n time. And that is problem F, and that is the rest of problem 2.